Bonjour à tous et à toutes. Je pense qu'on peut commencer. Donc c'est un grand plaisir d'accueillir Assa Auerbach, qui va passer un mois au Collège de France comme professeur invité. I'm going to switch to English to introduce him. So actually Assa doesn't need a very long introduction. He's very well known to our community of quantum condensed matter physics. He's the author of many works in fields as diverse as quantum magnetism, superconductivity, superfluidity, the quantum Hall effect, and so on and so forth. In fact, the Hall effect and transport phenomena will be at the center stage of his lectures here. Assa had started his career in the US. He was at Stony Brook and then at BU, and I think around the mid-90s he moved to Israel, where he's a professor at the Technion and has remained at the Technion since then. You may know that Assa is the author of two famous books. There is one, the famous yellow cover book on quantum magnetism and interacting electrons with Dana Rovas, which I'm sure all of you know. And he's also the author of an even more famous book, Max the Demon and the Entropy Doom, which has been translated in French. And I don't quite remember the French title, but I have it here. It's called L'Entropie Fatale, and it's edited at the CNRS editions. It's a cartoon book, and I enjoyed reading it very much. I even helped sponsoring it through some collaborative website. So, Assa, we are very glad to have you here, and we are looking forward to your lectures.
Thank you very much. Short statement. You can hear me, right? Okay. So, merci d'être venu à ce séminaire. Je suis très honoré de prendre la parole aujourd'hui. Je suis désolé que mon français ne soit pas assez courant. Donc, avec votre permission, je vais passer à l'anglais. Okay, so the subject of this is a kind of a general audience talk about the Hall effect, which actually has a bit of historical anecdotes about it. And what I want to show is that the Hall effect has been very important to characterize conductivities, metals, in the sense of understanding what are the moving parts that actually allow the electricity to go from one side to the other. Because if you ask this question, any person would immediately say electrons move the current in a metal. But the Hall effect gives you different ways of understanding the moving parts, which could be, as we'll see, other kinds of particles. So why am I interested in that? Because even recently, there have been materials and experiments that gave results for the Hall effect that were not understood. And it really boils down to the fact that what was not understood is what is the metal or the superconductor made of. And that's what I want to show. So these are, for instance, two Hall anomalies, so to speak, which I'll describe. One of them is appearing in superconductors, quite a large range of superconductors. When you cool below Tc, but in a strong magnetic field, the Hall effect seems to have a sign change that is not been well explained for many years. And the other case is the famous cuprates that have a high Tc superconductivity, but here I'm looking at very high temperatures, much above the superconducting phase, and then the Hall effect has this apparent divergence that again contradicts everything we know about metals, about Fermi surfaces, because it happens where there should not be any divergence, which is at half filling. So these problems go back in history, and as you can see, it puzzled people like Landau and Drude and Boltzmann and Maxwell, and I'll refer to that. So why is the Hall effect telling us about the moving parts? Because in experiments in high-energy physics, you exactly use very similar idea. You put charged particles through a magnetic field, and you watch whether they circulate clockwise or anti-clockwise, and this way you can detect their charge, and that's very common in bubble chambers. So the Hall effect is similar, except it's in a metal where you have lots of particles, not one, and they interact with each other. And the history that I like to show is very interesting because when Hall wrote his paper, he, first of all, very nice language, but he said that he was actually interested in Maxwell's ideas because he studied under Professor Holland in Johns Hopkins University, and he read this sentence that Maxwell said, that it must be carefully remembered that the mechanical force which urges a conductor carrying a current across the lines of a magnetic field acts not on the electric current, but on the conductors. In other words, Maxwell, who did not really understand solid-state physics the way we understand it now, didn't think that there will be any force on the electrons, on the current, but on the ions that carry the electrons. And what Hall did in his experiment is he actually disproved that statement of Maxwell. And here's the statement. When he describes his Hall effect, which is, of course, passing a current and then measuring a voltage drop on the transverse direction, and he sees that the effect was reversed when the magnetic field was reversed, and it was not reversed when you change the poles of the galvanometer from one end. So in other words, the phenomena observed was just we should expect to see if the electric current was pressed, not the solid around it. So that was the reason the Hall effect was considered an important discovery at the time. And it took a while to, as you say, to understand this effect. So when we explain this effect, to elementary students, that's the meaning of Physikerstein, it's the first course in electricity in the Technion, you actually cheat the students. You say, well, let us imagine that electrons are moving without interactions, without, sorry, I'm going back. Oh, I'm not handling this correctly. Just a second. Yeah, so we have electrons moving in like the continuum, and they see an electric field in one direction, a magnetic field outside the plane, and they move in the cyclotron orbits, classically. And there's a current that is related to the velocity and their charge. And that current is related to the electric field that we see here, this electric field, through the sigma xy, the Hall conductivity. And you want to calculate the Hall conductivity. You can say, let us move to the moving frame of reference, which is velocity v. And if you tune the velocity such that the electric field will go away, which will be c over b Ey, then all these electrons just move without, will just go in circles and not move at all. You'll have zero current, zero electric field. And then you ask, what does that mean about v? You plug this into here, and of course you'll get, just a second. Yeah, you move into the moving frame, and you'll get this relation that will say that the Hall conductivity is NEC over B. So you see the Hall conductivity will care about the charge, the sign, E, and about the density. And that result, of course, never applies in metals, which has impurities and has a lattice. But it gives you a sense of why the Hall conductivity tells you something about the charge carriers. So this explanation, of course, has been modified by, okay, so before that, there's a more sophisticated way of calculating sigma xy, which I will not discuss in these lectures, and that's particular to quantum Hall phases. These are quantum phases that you apply a very strong magnetic field, you change the nature of the electron correlations, and if you want to calculate the Hall effect there, it's convenient to use topological formulas like why doesn't it work? Yeah, oh, okay, it takes a while. The Chern formula, which is knowing the ground state wave function dependence on all kinds of Aronoff bomb field that are passed in the holes of the torus. So it's a mathematical identity that was proven by David Tallis and Yossi Avron. And there's another formula that one can use called the Streda formula that relates the Hall coefficient to some thermodynamic response. But these formulas, even though they're convenient for calculations, they do not apply unless you have these strict conditions. So one should apply them with care. First of all, you have to be exactly at t equals 0. So you're looking at ground state properties. Then you have to insist that the system has no longitudinal conductivity and no dissipation. And then if you are looking at a certain model, you have to see that there's an excitation gap that remains finite in the large system limit in periodic boundary conditions. And then there's essentially, in order to prove these relations, you have to take what's called the inverse orders of limit of wave vector and frequency that is demanded for DC response. So all these show that these formulas have limited applicability in metals, because metals have, of course, longitudinal conductivity, and one should use different formulas. So the history is that Drude, actually, was a German physicist in the beginning of the 20th century that thought that to think about electrons in metals is really to think about classical gases with no interactions. And classical gases have some scattering time called tau. And because of that scattering, you get both longitudinal and Hall resistivity or conductivities. And this is the tensor that is relevant to the transport, to the electrical transport. The longitudinal parts and the Hall parts are the diagonal, off-diagonal terms here. The longitudinal part does depend on the lifetime tau or between scattering events, the electron density and the effective mass. The Hall, notice, is depending on all these quantities and also on the magnetic field and on tau squared. So you see the Hall conductivity is very different than what we saw before in the lattice and impurity-free model. So one should realize that the Hall conductivity does have all these dependencies in it. But if one looks at the Hall resistivity, which is the inverse of this matrix, and calculated at weak magnetic field, you get an expression that all these quantities like m star and tau fall off, and you're left with a very simple expression, which is 1 over the charge density times velocity of light. So this is a relation that really makes the experimentalist use the Hall resistivity, not the conductivity, as a way of seeing how many charge carriers do we have and what is their sign. Now, this expression from Drude is actually quite general for band structures that are parabolic, which is below, for semiconductors at the bottom of the band. And the question that was always asked is, the funny thing about this relation is that it relates a quantity that you measure by essentially transport. And transport is a dynamical response function. It's something that has to do with time dependence. And you would expect it to depend on lifetimes and all that, but it doesn't. So is that a general property of the Hall resistivity? And the statement that I want to make is that, in fact, it is. But it's not this simple relation in general, but the fact that this coefficient is actually a thermodynamic coefficient, a coefficient that is determined by statics, by equilibrium quantities of the metal, is actually general.
Assa, maybe a question about this. As soon as you have one more band, right?
Then you have to add in parallel. You have to add in parallel the whole resistivity.
Ratio of lifetimes.
Yes. Or also, if you have two layers, because resistivity is non-additive. So if you have two layers and they have different Hall coefficients, then you have to know the difference in their sigma xx. So.
Right. But what I'm trying to say is that as soon as you have one more band,
yes,
the fact that the whole number is actually a transport measurement and not purely thermodynamic.
Okay, so let me qualify the statement that I'll show later. That's when you have a single component system. Yeah. Okay, so go back to history. So Heisenberg gave Peierls a problem to look at the Hall coefficients of metals. Why? Because, as I said before, the Hall coefficient of metals should be always negative if you have electrons carrying the system. But apparently there were materials like gold, silver, lead, palladium, and so on that had positive Hall coefficients. And he asked him why. And Piles worked on it, and of course he figured it out that when you fill up a band and you come close to the edge, effectively you should think of the carriers as holes, which are the parts that are missing to fill the band, and those holes will have a positive Hall effect sign. This is something that he wrote, and the reason it appears in the history of condensed matter is because he figured it out before Dirac figured out the positron. So it was in 1929 he figured out that metals have currents carried by holes, and Dirac used essentially the same idea to say that in his equations he had two bands, and he said, okay, let's say that the bottom band is completely filled, so you have, and there's a gap between them, and so the electrons are sitting on the unoccupied conduction band. But the other prediction is that if you take electrons from the filled band, you will actually create positive particles. And that was an idea that only became discovered in 1932. So according to, so Beth actually explained that Piles' work was unnoticed because nobody believed Dirac for a while when he had this theory of positrons. So it's just an interesting proof that condensed matter in many times gives inspiration to other fields of physics. Okay. Now, if you want to understand this Piles idea, you can look at electrons in a band. And this is just a general feeling. It's nothing special. You can think of the current as carried by all the velocities of all the particles. And the velocities, of course, are the slopes at each position. And because there's a symmetry, the same number of particles have a positive velocity and a negative velocity, this will have no net current. However, if you fill up, you put in one extra electron in one side, you get a positive velocity, you get a current which is equal to the electron charge times that velocity that you filled. Another way to think about the same current is in the whole picture, where you just say, oh, I have here a bunch of positive charges, and now I have one extra positive charge, and because it's sitting on this side, it has a negative velocity. So you have a negative velocity and a negative charge, a negative electron charge. So it'll give you the same expression. So the lesson from this is there's two ways of describing the same current. It's not that one is right and one is wrong. But when you look at a two-dimensional system, this is just a one-dimensional band structure, but in the 2 dimensions, there is a difference between the current carried by holes and electrons, and that is seen through the Hall effect. So the Hall effect is the one that tells you what is the right way of thinking about that. This is essentially an illustration of what is really moving here, right? The black or the shadows, or the birds. Okay. So let's go back to a history of metals. You know, Fermi surfaces describe the low energy excitations and the currents in metals. And if one has very weakly interacting particles, very weak scattering, weak disorder, one can, it's not really moving very well. Okay, so I go here. So if one looks at expressions for the whole resistivity from Boltzmann equation and band structure, you get this formula. It's in the textbooks, old textbooks of transport theory. This formula for the Hall coefficient is actually an equilibrium formula. It is one that is derived in the approximation that the lifetime doesn't depend on the position on the Fermi surface, but it's totally a geometric function that only cares about the curvature of the Fermi surface. And it will give you the sign of the Hall depending on whether the Fermi surface is a closed ball or it's essentially the ball of the Fermi surface, the sphere of the Fermi surface covers the empty sites. So you take a two-dimensional band structure and just a tight binding square lattice, and you'll see immediately that if you are, the Fermi surfaces are these curves. If you are filling the bottom electrons, bottom states, you get electron-like closed Fermi surfaces. And if you fill above half filling, it should be positive, and therefore the Hall coefficient with this formula crosses 0. No singularities anywhere in the band. There is a singularity at the bottom of the band and the top of the band at n equal 2 and n equals 0, but nothing in the middle. And that's a general property that you can add next nearest neighbor interactions. You can add many, many things to this theory, but the singularities are really determined by the empty or the full band. So once you see this, and this is with next nearest neighbor interaction, so what the next nearest neighbor interaction does, it moves the zero crossing from half filling to the left or the right, depending on the sign of the effect, because you can see the curvature now is, even at half filling, has the negative curvature in most places. So this is the well-known result that everybody uses and is modified by adding scattering rates that depend on k, but this singularity is still, the absence of singularity in the band is a general property of Fermi liquid theory. Okay, so once we realize that, we look at the experiments. And this is experiments in lanthanum, strontium, copper oxide, doped. So one has to understand that people plot this curve such that the electron density goes from the right to the left. This is the density of 1 electron per side, so it's half filling. So, as I said before, in the tight binding model, nearest neighbor, the Hall effect should vanish here smoothly, just go through 0. But the experiments show that it diverges with a positive number. Now, the fact that it's positive, one argued, comes from adding next nearest neighbor interactions, pushing the zero crossing to some value. So getting a positive number here is not necessarily a sign of breakdown of Fermi liquid theory, but the fact that it's divergent, and this is at quite high temperature, above any kind of a disordering transition or breaking of symmetries due to lower energy phases, is an anomaly. This is something that we need to explain. So, okay. So we come into the realm of strange metals. These are metals that, did I miss something? Yeah, no, I didn't. Okay. So this is a chunk of material called IPCO, high TC superconductor. You can see already it's a strange metal by just looking at it, because it doesn't look like a metal, right? It looks like some piece of stone that you found in the field. And you wouldn't expect it to be especially good conducting. And in fact, it's a very bad conductor at high temperatures. And it turns into a high TC superconductor suddenly. So what about this behavior, metallic behavior of such systems? So we noticed that if we just plot the resistivity versus temperature, it goes up and up and up in temperature. And if you cross this line, it's called the Offer-Regel line, it means that the distance between electrons becomes the same order as the distance between scattering. So you have no well-defined free electron theory, actually, to describe the transport above these temperatures. And I would claim even below this temperature, it's very strange because it looks like this criteria doesn't really affect the behavior at all. So this is part of the reason people call this bad metal, strange metal, all kind of derogatory names. But the point is that, okay, in this regime, one has to really try to solve any kind of a model that describes this regime. And one of the models that was suggested very early on by Anderson immediately after the discovery of high TC superconductivity was a model that captures the insulating behavior of the system at half filling. This is called the TJ model. This model actually describes the low energy physics of a more microscopic model called the Hubbard model. But if you notice, its degrees of freedom are very different from free electrons. Why? Because in every site, you can have either 0 or 1 electrons, but you're not allowed to have 2 because of strong interactions. It's called a Gutzwiller constraint. Now, why is that causing headaches? Because now if you move, let's say, the charge, which is now this empty site, by moving an electron into it, you would have an effect on the spin configuration that goes on around it, because you can only parallel transport the spins, and that will, after a charge moves around, the spins will become completely messed up. This is essentially spin-entangled charges. And they don't really lend themselves easily to Bloch wave theorem or to get the eigenstates as non-interacting quasi-particles. But the model itself is well defined. One can write it on the lattice, and one can try to solve its transport properties. And that's what I want to do. So it really describes a system that is close to a Mott transition. Why? Because if you fill up one electron per site, as you can see here, if you filled up all these electrons and you don't allow double occupation, all these electrons become stuck. And this is actually in the regime where band theory tells you this, you have the large Fermi surface and it's a very good metal. So getting all the charges to get stuck at half filling is called the Mott effect. Now, to calculate the conductivity or the whole conductivity in that regime, we needed actually to develop some new formulas in quantum transport theory. It turns out that for the Hall coefficient, as I said earlier, there is an expression given in terms of two terms, and that expression can be calculated in a much easier way than calculating what's called the Kubo formula, which is the usual way people do calculations for model Hamiltonians. I will describe this in more detail in a tutorial session, which I'll explain how to derive it and also other aspects of simplifying the Kubo formula, which is the original formula, which I don't show here. And that is really the reason that results could come out. Because prior to this expression, people had very difficult time evaluating transport coefficients due to problems of numerics. Well, I'll mention the problems soon. But this expression here essentially contains, if you want, three quantities to calculate. One of them is called the current magnetization current susceptibility. It's a thermodynamic susceptibility of the Hamiltonian. One is the conductivity sum rule. It's well known. It's the optical conductivity sum rule. And another is a correction term that is actually complicated. And the main goal is to evaluate it, estimate it, and see if it's large enough to change the results we get from this term. And that's necessary to do. But we found already after experience some conditions on which we can bound this by calculations, by numerical calculations. So the formula is containing only terms that are equilibrium coefficients. They're computable by many different methods of statistical mechanics that are not applicable to dynamical transport Kubo formulas. High T series, Monte Carlo in imaginary time, variational wave functions, and so on. So it lends us, there's a whole bag of tools that statistical mechanics, equilibrium statistical mechanics has given us that we could use to evaluate these quantities, and also the correction terms. So we don't need to calculate linear real-time response functions at long times. We don't have to do analytic continuation. We don't have to impose some phenomenological scattering rates, uncontrolled proxies, and so on. So this is the advantage of this formula, and I will show you the results of this formula applied to the TJ model. Okay, I'll give a tutorial on this. Hopefully some of you can come. This is the result. So I'm comparing my results to the non-interacting theory, the theory which has no interactions, which is the usual, or weak interactions if you want, weak scattering, which is the theory that can be applied, the Boltzmann equation and diagrammatic perturbation theory and so on. That theory will tell you, for the tight binding model with no next nearest neighbor interaction, the Hall effect is totally negative. It diverges, as we said, in the bottom of the band, and it crosses zero, that's the white area, at half filling. And you can understand all the metallic behavior in such a non-interacting model with the Fermi surface. On the other hand, the TJ model, which close to half filling really is described by these projected holes, has a completely different behavior of the Hall coefficient. First of all, the sign gets reversed already at quite high doping. Okay, so the effect of the Mott phase, this is a Mott insulator that doesn't allow the electrons to move, is quite deep into the phase diagram. So I'm talking about high temperatures relative to the hopping rate and also relative to any kind of magnetic exchange and maybe superconductivity at low temperatures. And in this regime here, you get a very different behavior. So you get this anomalous behavior I described that was observed experimentally, but it has far-reaching implications about how we understand the low-temperature physics. Because as usual in metals, we understand superconductivity by understanding the normal state and pairing the quasi-particles of the normal state. Here, in order to understand any low phase, it could be superconductivity that is predicted in some variations of the model to exist, or charge density wave, as Antoine has found. Those would be composed out of the charge carriers which exist at high temperature. And if the charge carriers are highly entangled vacancies with a positive sign of the Hall, that really means that one should abandon thinking about Fermi surfaces and so on. That's my opinion. But anyways, this is the result. And one would like to understand, why is the Hall sign reversed? And why does it behave like a semiconductor at zero filling when in fact it's close to half filling? And
just to make sure I understand. So
yeah.
Here we are talking about temperatures which are larger than the hopping.
No, with the Monte Carlo we went down to up to order J.
Okay.
There's still no minus sign problem there. And so the Monte Carlo is fine there. Anyway, so then there wasn't much of a change between T and J. This is a different system that is relevant to people who do cold atom experiments, actually experiments that were done on these systems without a magnetic field, but just the phase diagram found that when you take bosons, atomic bosons sitting on some kind of an optical lattice, and they have interactions between them, and you make the barriers large enough so that the interactions are strong between two bosons on the same side, or n bosons on the same side, that system will have these Mott phases, where if you have one exactly, or two or three bosons per side, the system becomes insulating, or becomes essentially a gapped insulator that charge cannot move, or density cannot move around. Now, this is the phase diagram in the density versus interaction strength at low temperature. And it's quite simple. You have these Mott lines. These are lines, like we have in the TJ model, of an integer number of particles per site. And what we found, calculating Chern numbers and the series of papers here, and also using the formulas recently that I showed before, that between two Mott lines, you have superfluid. You have essentially a superfluid of bosons, but it's different than the superfluid that you get in the continuum, like in helium-4, because you have a lattice, and the lattice is very strong, and there's strong interactions on the lattice. So what you get is, between two Mott insulators, you get a sign reversal of the Hall exactly halfway between two Mott insulators. And that comes, okay, I'll show you the calculation here. Yeah, so this is the calculation using our formula. This is the Hall conductivity. Oh, why do I have it? Oh, I'm sorry about this. This doesn't work very well. Okay, so what you see here are the line. I don't want that. Yeah, the line here. Why does it? I didn't touch that. Okay, I won't use that. I use a stick? No, never mind. Yeah, the three lines are actually the sign of the correction term. I told you the correction term is complicated to calculate. In fact, very complicated. But what we see is that when we add the second, it's a sum, but we add the first term, which gives you the second order, and then the other 4 terms that give you the, or 6 terms that give you the 4th order, the lines don't change very much. Qualitatively, it looks quite the same, even when you look at the lowest order calculation. So this is an example of application of the formula, but what it shows you that you have a whole sign change at half filling in these hardcore bosons. And that's actually something that has not been confirmed experimentally because of the difficulty of applying an effective magnetic field on cold atoms, but maybe it will be possible to do that somehow. Anyway, so this is an interesting effect of the Mott phase changing the nature of the carriers. Because if you want to kind of get the bottom line of all this picture, you have particles, and it doesn't matter now if they're fermions or bosons. There's strong interactions between the particles, and they induce hardcore constraint. So if you think about hardcore particles moving, then you see that if you have a minority of sites occupied, then the motion is carried by the particles. But if you look at a system where there's more particles than holes, and you move the particles, then now you see that, your eye at least, that what is moving are the holes to the left, which is the same current, but that's really what the Hall effect is doing. It tells you what are the minority carriers in this case. So the Hall sign is determined by the minority of particles versus vacancies when you have this Mott physics, this interaction physics dominating, and not, let's say, band structure physics. Okay, so I finished this part of the talk. How much time do I have? I don't want to...
You still have about 20 minutes.
Okay, so this is another system, but again, the Hall coefficient will tell us interesting things about that system. It's a system of a superconductor. Superconductivity, again, I'm being kind of general here, explaining what I think is most important to know from superconductivity. Superconductivity is a property of an electronic system or a charge system when you bring close to it a magnetic field. And the magnetic field increase will cause the system to have a persistent current. And you stop the magnetic field, the persistent current stays. It's completely induced by this gauge field or the Aronow-Bohm flux that you shoved into the system, and it stays there. And that is actually a rigidity, because if you put an integer number of flux quantum in here, you could completely unwind that current and get it go to 0, but the system won't. The system will remember how it's prepared. It is not Galilean invariant. It remembers the lab frame that it was prepared. You put a magnetic field, it comes into an excited state of a current, which could be very high, you could have mega amperes in there, and it will stay there indefinitely if the system is large enough. So that rigidity is very important to understand transport behavior. This is actually an interesting experiment done at Haifa by Amit Keren's group. He's taking a very narrow solenoid, which is like an Aronow-Bohm flux, and he's cranking up the current, and he's getting a persistent current to flow, and he can measure that persistent current, and it will tell him how stiff is the material, or what is the superfluid stiffness, which is related to the London penetration depth, but he can measure it even in systems where the stiffness is very weak, like close to TC. Anyway, so that's just a statement about experiments. So the theory says that the current is really now carried not by single particles hopping around, like in Drude formula, but by this gradient of a superconducting phase of the order parameter. And the persistent current is really just like having a stress on a mechanical spring when you put torque on it, and it will keep the stress indefinitely unless you break the spring. Okay, what is vortex matter? Vortex matter is you take a superconductor, you apply a magnetic field to it, you make the system very thin so the magnetic field penetrates uniformly into the film, and that creates vortices. What is important is because of the stiffness, because of this property that I talked about, It doesn't allow any number of vortices. It allows exactly the number of vortices to be equal very, very closely to the size of the magnetic field. That relation, which is essentially saying the vortex lattice is incompressible and it's completely determined locally by the field, is something that will tell us how many vortices we have if we put a field on a system. Okay? These are vortices of the supercurrent. It's not flux tubes, you know, of the magnetic field. Josephson relation tells us that if a vortex moves, then you get a phase winding, which is equivalent to a chemical potential difference between the two sides of the system. So that's showing how the phases move. And you see the top part is rotating, the bottom isn't. The relative rotation is the chemical potential difference. And that is very general. So these are the two things one should know. And now you look at materials, and many materials have this phase diagram. This is like a high TC cuprates, but it exists in many systems. You have the magnetic field and the temperature, and you have the vortex lattice phase. But if you make the magnetic fields too large, or you make the temperature higher, the vortices will start moving. That lattice will melt. It will still be incompressible, but it will have relative motion of the vortices like an incompressible vortex liquid. In this regime, you get a finite resistance. So this is not superconducting. In fact, in terms of transport, it looks very similar to a metal. Usually people put some kind of a line between them. It's very difficult to determine that line in many cases because it's a crossover where the vortices touch each other, and they call it HC2. But what is interesting is that this flux flow regime, one really has to consider the fact that the vortices feel each other. They still, at short range, there's rigidity, and they repel each other quite strongly, and that's not a property of metals. So there is a difference in the transport. Now, one wants to understand the transport in this regime, and Bardeen and Stephen did that many years ago. They wrote a theory that says that if you go and perpendicular from high field to low field, you go from the normal state where you have some resistivity, and then at this BC2, nominally it will go down linearly with B with the magnitude dependent on the normal state resistivity. That's the longitudinal part. Now, with the same theory, they also stated that the whole resistivity will have a B squared dependence and then cross over to B, and that is Bardeen-Stephen theory for the whole resistivity. What is important in their theory is that the sign of the Hall coefficient in the flux flow and outside the flux flow is the same. Experiments that show reversal of sign is definitely in violation of that idea, of that theory. So that caused a lot of confusion, lots of papers, and lots of arguments in the literature over the years until people got tired. But it was still, I think, in many minds, an open question. What would make the Hall suddenly decide to change the nature of its carriers from positive to negative? And as you can see, it happens. It happens in electron dope, in hole doped superconductors, electron doped superconductors, and vanadium films, and many, many other systems. I saw it in molybdenum sulfide. Many systems have it. They have to be thin films, and sometimes disordered, sometimes less disordered. But this is an open problem and an experimental find. So I'm just showing a small sample of the papers written by very well-known experts. And the whole sign change in different systems acquire different theories. But actually, it seems to be quite a universal phenomena close to TC. The problem I'm writing here is so much not the problem of the experiment, but the problem of the theories that use Vortex Dynamics. What's the problem with Vortex Dynamics? Because Vortex Dynamics says that one can think of vortices as subject to a force coming from an external bias current. So this expression here, well known from hydrodynamics, will tell you that if you put a bias current in a system and you have a vorticity, the vorticity will have a force on it wanting to move perpendicular to the current, but perhaps it won't move perpendicular. This depends on the tensor called viscosity tensor. So if you know the direction and the magnitude of the velocity introduced by the current, you can translate this to an electric field and solve the transport problem of current versus electric field. The problem is this eta. The problem with eta is there's no microscopic calculation of eta. There are, just a second. Why does it do it to me? Okay, the longitudinal part you can relate to normal state properties by using Joule dissipation, because there's a dissipative response. There's heat generated from the diagonal part of the viscosity. But the off-diagonal is, actually it should be negative on this side. The off-diagonal part is non-dissipative. And if it's non-dissipative, one should have a microscopic theory to calculate it, like the Hall effect. It's not something that you can guess from other experiments. And the problem is that there's no Kubo formula for that, because there's no way the theorists can actually calculate a voltage as a function of applied current. You can take a Hamiltonian, you can put fields on it, but you can't force the system to have a current. Now, there's only a very special case that you could do it, which is non-interacting electrons in the Landau formula or something like that. But in general, if you have a many-body system and you want to do a computation, you put it on a finite boundaries, open boundary condition, this is a serious theoretical problem. But the upshot of all that is that there were huge arguments about this eta Hall. So we decided to revise the theory and look at it in a different way. And the different way is actually more natural in terms of linear response. We look at a superconductor, we apply a magnetic field, we create the vortices, and we put a voltage. And then experimentalists would be immediately shouting, you're going to make a short, right? A superconductor. You apply to it a voltage, the system will have a linearly increasing in time current and will burn the fuse, if not something more. However, there's another option, especially in the flux flow regime, which is that the vortices will move. Now, if the vortices will move, that will create this EMF, the Josephson coupling that I showed before, and that will essentially be exactly the EMF that will be the same as the voltage drop that you have here. And you'll have a finite current, not an infinite current. Now, the only steady state that will allow you to have a finite constant current must obey a very precise relation between the velocity of the vortex and the electric field with no parameters of material inside. This is Josephson's relation, but turned on its head. In other words, here I know E and B, and I tell you what V is exactly. What is nice about V, it's completely in the Hall direction, so the velocities of the vortices are perpendicular to the electric field, but you haven't solved the transport problem unless you give me the currents. So you have to calculate both the current, the Hall current and the longitudinal current, knowing that the vortices are moving with this particular velocity, okay? So that's really the way to think about it. So now the question is, what is the current? And this is done in this paper with Dan Arobas. I'm having a hard time here. So each vortex is creating an EMF, but all the vortices together are creating essentially the electric field that we said before has to be the same electric field that's measured outside. But inside the core, the electric field is stronger because there's a relation between the total electric field and the inside electric field coming from theory of polarization. But anyways, what we will assume as a model is that inside the core, which is size psi we said before, the transport is metallic, given by local conductivity, which is very close to the conductivity or extrapolated on the conductivity of the normal state. And this will give us essentially this expression for the conductivity, not resistivity. So notice that we have a term that is exactly the term that we get from Bardeen-Stevens theory. So we cover Bardeen-Stevens theory for the term that comes from these cores. So these cores are now ideal current pumps, okay? And we know what the EMF inside them is, and using this expression we know what the current, and the current is flowing in a laminar way in the superconductor, so you have no vorticities, and therefore you know exactly the total current density that is produced by these current pumps. And that's the Bardeen-Stevens expression. So it's very simple. But there could be another contribution. What is that contribution? Let's imagine that each vortex attracts some charge to it. Notice the vortices are moving perpendicular to the electric field, so that will be a Hall coefficient, Hall conductivity. And it's given in a very nice and simple way. It's the Cooper charge 2E times the charge attached to the vortex divided by h. So it's an expression like E squared over h you get in the quantum Hall effect. And that expression here is the reason you can get a Hall sign reversal. Because if this Q is different sign than this sigma of the normal state, you would, if this becomes larger than that, you get a Hall sign change. And the question is, what is this Q? And there's been arguments about vortex charge, so I want to show what we're saying here. This is actually nice in terms of theory of transport. So imagine you have a condensate of moving vortices. And in every vortex center, there's a depletion of charge, let's say. That's the usual case, because the kinetic energy of the rotating currents around the vortex would actually push out charge to reduce the energy. And if you have that condition, you get a charge depletion QV. And notice that you have a motion. And the question is, what is the current associated with this motion? So one would say, oh, it's just the condensate density times the velocity. The question is that right? So that means, do the vortices drag the whole liquid behind them or not? So the initial statement is maybe yes, but the answer is no. What is dragged is only the depletion, only the part of the charge that is related to the positions of the vortices that is created essentially by the vortex existence that moves with the velocity v. And then the current is going to be QVV, will have actually the opposite sign to if the whole condensate moves. So this is a serious problem that when we published the paper on SciPost, actually on purpose I did it on SciPost because I wanted to get good referee reports of people who really want to understand. And the point is that there was a misconception in the field, and it still exists, that when you drag a vortex, you move the whole condensate. Now, the reason it's not true is because it's not a classical liquid. And I'll show you the difference between a classical liquid and a superfluid. Okay. Its momentum cannot be imparted on a superconducting condensate by slowly moving potentials, and you cannot drag it. In other words, if you move a potential, and a vortex position is like a potential, it's coming from the fact that the Hamiltonian has essentially a vector potential that tells you where the vortices are, and when you move that potential, you will not move the superconductor because if you do it slowly enough, because the superfluid is rigid and attached to the frame it was prepared at. So this is known, okay? You cannot row, for instance, on a superfluid lake, okay? The oars will not move the boat. The oars will just go through the superfluid. You might have oscillations, time-dependent oscillations, but you won't have a motion because you can't give the superfluid a momentum if you're doing it slow enough. It essentially wants to keep its zero momentum state. So that's an example of trying to swim in a superfluid or fly in a superfluid or anything, fly an airplane in a superfluid. You can't because you won't have all these possibilities of essentially creating vorticity to give you a way of putting a force on the superfluid. So this is a counterexample on a classical lake. Oh, I wanted to show you the movie. Why doesn't it move? No, maybe I'll do it here. Yeah, so you see that in a classical lake you can impart momentum to a lake quite nicely. Okay, now the charge itself, there's another problem. The charge itself on each layer is completely neutralized within the layer if it's, I'm just going to stop using it. Within the layer, it's completely neutralized. But if you have a layer and a dopant layer on two sides, or if you have a very thin film and you can push out the charge from the superconducting layer to a third dimension where the charge is parked, it'll be like a semiconductor where, you know, the dopants don't live on the same layer as the 2-deg, and then you have currents of electrons where the dopant don't move. So if you get to that situation, then you'll have a Hall current. And we calculated from the experiment what is the size of the vortex charge that these experiments are give. So you have to invert the matrix of rho xx and rho xy to get sigma, and using this expression and subtracting the extrapolated value from the high temperature, we got the vortex charge, and we plotted how it depends on magnetic field, and it depends logarithmically as expected. And the overall magnitude, just for interest, of the vortex charge per layer is about 1 electron per vortex. So 1 electron per vortex is a very small charge, difficult to detect, especially on metals, but hopefully somebody will succeed in doing it. I know that people in Weizmann and Hebrew University are working on it. Amir Yacobi in Harvard said he might think about it, but it's difficult. But that is essentially an independent check of this theory that would be interesting to see the sign and also the magnitude of the vortex charge. So this is the reason you get the Hall coefficient. The charge is generically opposite in sign to the Hall coefficient, and that's what's moving in the flux flow regime. So I think I can summarize now. So the Hall effect exposes the moving parts of conductivity, and the Hall sign reversal can occur from lattice potential, as Peierls and Dirac were mentioning, near a Mott insulator because of restricted hopping, and in superconductors flux flow by moving vortex charge. And there are some new formulas that I will explain in a future lecture that will extend ourselves beyond the Landau-Boltzmann quasi-particle regime where you can use existing formulas. And that's the summary. Thank you.